Hello everyone. We will finish chapter 4 today. However, before we get started, let's review the content in the last class, the first part of chapter 4. In chapter 4, the topic of chapter 4 is numerical summaries. And as we can easily notice from its name, we will find some numbers from the data distribution which can represent the data distribution. So first, we saw the representative values for these centers. With this example, we have 65 instances and these numbers varies from 0 to 99. And the most simple and naive choice of the representative value for this center is the arithmetic mean. And we can easily calculate the arithmetic mean by sum all of these values and divide it by 65 in number of instances. However, if the data distribution is symmetric, the mean can be used to represent the center of the data distribution. However, if the data distribution is asymmetric, for example, if it is right skewed or left skewed, then the mean is affected by the extreme values in the tails here. So mean is shifted toward to these extreme values. For example, for the right skewed distributions, the mean is shifted to the right, and for the left skewed distribution, the mean is shifted to the left. So the mean will be located here. It means that more than half of data is less than mean, and less than half of data will be more than mean for the right skewed distribution, and for the left skewed distribution, less than 50% of data will be less than the mean, and more than half of this data will be greater than the mean. So the mean is not well representing the data distribution in these asymmetric distributions. For the extreme example, we have, for example, one. We have some data distribution one. We have 9 ones. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we will add comma here. And there one more data which has the value of, for example, 10. Okay. So in this case, the mean of this data distribution is 19 over 10 is 1.9. So it is the data distribution seems like this, you know. So it's very asymmetric and it is highly right skewed. It means that we have the extreme value in the right side. So in this case, only one data, only one data point is greater than the mean. Only one data point here, it means 10% of data point. And the remaining 90% of data points, these ones are less than 1.9. So in this case, this 1.9 may not be good choice to represent these data points. So in the exploratory data analysis, the median is more preferred to the mean because exactly the half of data will be less than the median and exactly the remaining half of the data will be greater than the median. So median is more widely used as the representative value for the center. So median can be calculated like this. If the number of data points are odd, we can choose the center point, center the data point because there are one center data point. However, if the number of data is even, there are no centered data point, and we can choose two data points that are nearest to the center, and we can take the average of them as the median. Okay. And median also has a property that the depth of it is the largest among the others. In other words, the median is the data point that has the largest depth among the all data points. So we can calculate the median and mean for the example here. And the important difference between the here mean and median is that mean is affected by the extreme values because it uses the attribute values or values of the variables. However, the median only uses the ranks of the data points. It does not use the value of the data points. So it does not affect it by the extreme values. Okay, it is less affected by the extreme values. Okay, so this one is the important property of the median. And the next topic was the representative values for the variation of the data distribution, because if the two here's the example here, even though two data distributions have the same mean, their distribution can highly be different due to their spread or their variation in the data distribution. Okay, so here there are two data distributions with 10 samples. The first distribution and second distribution have the same mean. X bar here is 50. However, the first one has the standard deviation of 7.4 and the next one has 13.2. So we can easily find that the latter, the second distribution, is more widely distributed than the first one. Okay. So to explain the data distribution, the one value, the representative value for the center is not enough. So we need another representative value which can explain the variation of the data distribution. So the examples for these types of representative values are variance and standard deviation and other quantiles such as quartiles and percentiles. So with this representative value for the variation, we can easily find the we can easily get more information for the specific location of a certain data point. We made this example in the last class. With the same mean and same data point, the location or the relative rank of this data point can be different by the standard deviation. Okay. So it is really important to understand not only mean, but also its standard deviation of the data distribution. However, we all know the variance and standard deviation. I will skip this part, most of this part. The variance and standard deviations, however, they are affected by extreme values, like mean. So, like median, we need another measure for the variation which is less affected by the extreme values, or in other words, which uses the ranks of the data points rather than the values of them. So we saw the definitions of the quantiles. Quantiles are the measure for the variation of the data distribution, which uses the ranks of the data set, and so they are more robust to the extreme values than the variance or the standard deviation. So in the last class, we saw the hinges or quartiles. They are the values. Okay, if the data points are ordered in their ranks in the ascending order with their values, the centered value, the data point at locates at the half of data are called median, we know. The hinges are the data points or the values that locate the 25% point here. And this one, 25% from the minimum, is called lower hinge, and 25% from the maximum is called upper hinge. And the way to find the hinge is using the depth of hinges. The depth of hinges can be defined as like this. Because the hinges are the median of the half of the data point. For example, the lower hinge is the median. Actually, it is the median of the lower half of data. And the upper hinge is the median of the upper half of the data. So the hinge, the depth of hinge can be considered like this because instead of the number of data points, we can use the depth of median here. So we can find the depth of hinges. So for this example, the n is 65, depth of median is 33, so the depth of hinge is 17. So if we find the points whose depths are 17 are, we can find 2 points. The first one is 33 here, and the next one, this is the lower hinge, and 58 here, this is the upper hinge. The way to find the points that having a certain depth is just counting 17, for example, here. And this is the 17th point from the minimum, and this is 17th point from the maximum. Okay. And from these hinges, we can also observe how the data distribution is asymmetric. So we define skewness with the hinges and medians here, like this. We use the difference between the median and hinges. For example, HL is here, HU is here. If this one is greater than this one, then we can easily find that it is leftly skewed, like this. And if this M is here, HL is here, and HU is here, then we can easily, maybe we can easily understand that it is rightly skewed. So this skewness with the hinges is defined like this. So if it is greater than 0, we can easily understand it is right skewed, and it is less than 0, it means that it is left skewed, and the value of this skewness is -1 to the 1, and if it is 1, it is very highly rightly skewed, and it is -1 if it is very highly negative skewed, and if it is 0, it is symmetric or not skewed. And we define the 5-number summary here. 5-number summary is one of the most basic numerical summaries of the data distribution. If we see these 5 numbers, we can get any information about the data set, which contains the minimum, lower hinge, median, upper hinge, and the maximum value here. Here, the skewness is given as -0.2, so it means it is slightly left skewed. And this is the 5-number summary. And okay, let's start today's topic from here. In the last in the last class, we saw the quartiles. Okay, which is the quartiles, which actually is 25% or 0.25 location. Okay. So in this manner, if we define 50% quantile, we can easily think that this one is the median. Okay. And 25 quantile is the quartiles and hinges. We have 2 hinges, HL and HU. Okay. So we call these kind of quantiles as P quantiles. Here P, we will put the values from between 0 and 1. For example, median is 0.5 quantile. and hinges or quartile. 0.25 quantile. However, we can use any of p between 0 and 1 here. So we can define 0.125, the half of the quartiles. Maybe we can call it maybe octiles. 0.0629. Or we can define any other numbers. 0.1, 0.2, 0.10347. We can define any p between 0 and 1 here. So in this page, we have 4 examples. Median, 0.5 quantile, and quartiles or hinges, 0.25 quantile, and E, we have 2E, EL, and EU. They are 0.125 quantile, and D, 0.0625 quantiles. These values are used for the numerical summary table, which will be shown in the last part of this chapter. So these are the examples of other p quantiles. Here is the value of the p here. And this QP here means the QP means the data points at the locating at P's point. So we can easily think like this. If the data points are ordered with its value from the minimum to the maximum here, the median is the the depth, which has the maximum depth n plus 1 over 2 here. And we saw the hinges here, HL and HU. They are actually the median of this lower half and the median of this upper half. Okay. And we can define L U here. So this EL is the median of this part, the most lower quarter, and the EU is the median of the most upper quarter, and DL and DU can be defined the same way. So the depth of median, we use the small depth of the median is n plus 1 over 2, and we define in the last class the depth of hinge is defined as Gauss dm plus 1 over 2. So with these definitions and with this definition, we can define depth of the E like this. E H plus 1 over 2. And the D can be defined as the E 1 over 2. Okay? So with the example of the exams course, let's make it here. N is when N is 65, D M is 33. So 33rd data point is the median, and the H is 17. It means that the 17 points from the minimum and maximum are the lower hinge and upper hinge. This is 9. It means that the ninth data point from the minimum and maximum are the EL and EU respectively. And finally, the D is, if we put 9 here, 5, the fifth point from the minimum and maximum are the DL and DU. So let's go to this example. Okay. EM is 33. The H is 17. The E is 9. The D is 5. So the 33rd point is here. This one is the median. And 17th point is here. This is HL. And 17 from the upper side, 15, 16, 17. This one is the HU. Okay, and let's find the EL and EL and EU here. So EL is the ninth point from the minimum. 1, 2, 3, 4, 5, 6, 7, 8, 9 here, 23. This is the EL. And 1, 2, 3, 4, 5, 6, 7, 8, 9. This one. 73. This is the EU. And the fifth point is DL and DU. So 1, 2, 3, 4, 5. This one. 18 is DL. And 1, 2, 3, 4, 5. This one. 78 is DU. Okay. So we can make many p quantiles like this. However, then how can we calculate the depth of, for example, p equals to 0.1? How can you calculate the depth of these p quantiles? So for that case, we can use this formula. There are many ways to find the p quantiles. However, in this textbook, we will use this definition. Pk is k minus 1/3 and over n plus 1/3. Here k is actually the index of the data point. So for example, we put, and n is the number of data points here. We put 65 into the n, and so the p, k is 0.5. Then 0.5 equals to k minus 1/3, 65 plus 1/3. So if we solve this equation, 32.5 plus 1/6 equals to the k minus 1/3. So k equals to 32.5, and 1/6 and plus 1/3 is 1/2. So this is the 33. We get the depth of the median like this. So if we put the p that we want to get here, then we can get the number, the index of the data point here. So if we want to if you want to put p here 0.5, and when n is 65, then it tells us that the median is 33rd point of the data distribution. So in general, if we put p equals to 0.5 and we make it n here, just n here, n over 2 here, so in this case, k equals to n plus 1 over 2. Okay? So we can get the same value with the definition of the median. And vice versa. If we put k here, so we want to know what is the percentage of the data points when we know the data index. For example, we have the 65 data points and we are curious that the 33rd point, what is the location of the 33rd point in this data distribution? Then we can put 33 here, k, and this n will be put here, then we can easily get p of k is 0.5. So this is the formula that can exchange the percentage location of the data and the index of the data. So if we want to know 0.1 quantiles of the data, then we can put just 0.1 and we put n here and we can get k. So in this case, the case data point is the p quantile that we want to get. So, and it is also well known that all the p values between 0 and 1, there are the corresponding k values so that we can easily find the index of the data point. However, there is a severe problem when the k is not an integer. So in general, k is not an integer for most of the p values. So if k is not the integer, then we need some interpolation here. So when p is given, then kp can be found like this. Kp, if we solve this equation, kp can be calculated like this. And p plus 1 over 3. So this is generally not an integer. So for example, this one, if we get 10.5 for this k, then there are no 10x 10.5. So in this case, we need some interpolation here. So we define okay, let me explain what the interpolation is and how the interpolation works. So for the non-integer numbers, there are two nearest integers, which is here the k1p, which is defined as Gauss kp, and the next one is the k2p, which is the k1p plus 1. For this example, okay, let's assume that with generality, let's make it 10.2 here, okay? So in this case, k1p equals to 10 because k1p is defined the greatest integer, which is not greater than this value. And k2p is 11, which is the K1P plus 1. Okay, then we will mix. So we will get the x 10.2, the imaginary value. We will use x10 and x11. So we will get this, okay, for example, the data point QP. We will use x, we will combine x10 here, x10 and x11 with some weight like this, 1 minus w and w. And w is defined as the difference between the Kp and K1P. Okay. The meaning of these weights like this. Here's the 10 K1P and 11 K2P. And here's the 10.2, which is the Kp. Okay. So here are the value of x10, here is the value of x11. Then interpolation means that to find the value between these 2 points that makes the line segment connecting these two. So then the value for 10.2 is defined by projecting this 10.2 to this line segment. Okay, so this is actually the combination of all weighted average of x10 and x11, and the weights are defined where it locates. For example, 10.7, like here, it will be more close to the x11, and 10.2 will be more close to the x10. So the weights are the inverse from the distribution, the distances from the nearest integers. For the 10.2, the distance between the 10 and 10.2 is 0.2, and the distance between the K2P and Kp is here is 0.8. So these distances are inversed. So for this K 10.2 to P is 0.8 multiplied by x10 plus 0.2 by 11, x11, because actually 10.2 can be defined as 0.8 multiplied by 10 plus 0.2 multiplied by 11. Okay. So if Kp is not the integer, we can use this interpolation formula, and the weights of these values are the reversed distance from the nearest integers. So with this formula, we can redefine the p quantiles of this one. It is slightly different with this definition. So with So with this formula, we can get new p quantiles of the data point. The median is the same. However, the quartile is, if was originally 17, it is changed to 16 plus 2/3. And 9 becomes 8.5, and 5 becomes the 4 plus 5 over 12. Okay. So because this is the integer, we actually do not need to apply any weights here. We just can use x33 as a median. However, for the remaining 3, we need to interpolate. So 16 and 2/3 are, we need to interpolate the values of x16 and x17, and the remainings are the same. We need to interpolate the value for the x8 and x9, and x4 and x5 here. So we can get the weights like this. So if we put the weight here, so it was originally 16 and 2/3. So these 2/3 will be the W, so 1 minus W here, so W here. So 1 minus W, and KP1, K2P, K1P, and K2P, K1P, and K2P, K1P, and K2P. Here are the 1 minus weight and weight. We can get the values. They may be slightly different from the original ones. Okay. These are the P quantiles. And let's go back to the here. Not here. Okay. They are actually the P quantiles that we can get the values here. And this is the last topic for today's class, the numerical summary table. The numerical summary table contains the values of the M, H, E, and D, and the end. End means the minimum and maximum. And there are 3 major columns: the summary, mid value, and the spread. Okay. So summary has 2 values, the lower value, upper value. The median has only 1 value. Okay. Lower value, upper value, lower value, upper value, minimum, and maximum. And mid values are the arithmetic average of these 2 values, and the spread is difference of these 2 values. So with our example, we can use the numerical summary. We can make the numerical summary table like this. Median, hinges, ED, and endpoint. So their mid values can be calculated like this, and their spread can be calculated like this. So these numerical summary, to make the numerical summary tables, we need to calculate, we need to record actually the 9 values here: median, lower hinge and upper hinge, EL and EU, DL and DU, minimum and maximum. If we get these 9 values, then we can calculate the mid values and spread from the summary values. So with this numerical summary table, okay, let's see if we see the trend or movement of the mid values, how the distribution works, because the mid values becomes larger. So we can easily find the asymmetry of this distribution can be inferred. It was actually for maybe this one shoulder part, it will be slightly leftly skewed. However, if goes more down and down, it will be slightly rightly skewed. Okay. Like this. So with this part, it is leftly skewed. However, containing this part, it is slightly rightly skewed. Because from the median, the mid value trend is becomes to move to the left and right again. Okay. And from the trend of the spread, the kurtosis of the data distribution can be inferred. So if the spread becomes, okay, spread always becomes larger. However, the speed of this becoming larger is high, then it means it is highly peaked. If the spread, the speed of the spread of becoming larger. However, the speed of becoming larger for the spread is less than it means the distribution it seems like this. It is the negative kurtosis or the leptokurtic. Not leptokurtic, platykurtic. And this is the leptokurtic. Anyway, so it is the high peaked and fat tail, and this is the lower peaked and thin tail. Okay. So these high peaked and fat tail are usually defined compared to the normal distribution. So if we make the numerical summary table for the normal distribution, then we can understand this spread change is faster or slower than the normal distribution. In other words, it is high peaked or fat tailed, or lower peaked and thin tailed compared to the normal distribution. So here, this is the numerical summary table for the normal distribution with mean mu and variance sigma square. So, oh, the this is the errata here, oh, critical errata here. This is the actually 1.150 1.150, and this one is the 1.535 1.535. Okay. So because the normal distribution is symmetric distribution, the mid value does not change. Always, it remains always as mu. And the spread for the normal distribution is the spread for H is 1.35 sigma, and spread for the E is 2.3 sigma, and the spread for the D is 3.07 sigma. So first we need it is we can easily find that if the sigma is large, the spread of the normal distribution becomes large. However, we need to define the kurtosis as the speed of changing the spread. So the kurtosis of from the numerical summary table, it is defined as in two ways. The ratio between the spread E and H and the ratio between spread D and H. So for the normal distribution, the ratio of spread E and H are 1.704, and for the ratio spread D and H, the normal distribution has the value of 2.274. So we take out these values from this ratio so that the kurtosis of the normal distribution becomes 0. So we use this formula. We can compare whether the distribution is high peaked or less peaked compared to the normal distribution. This is the example for the uniform distribution. Uniform distribution from mu minus alpha to the alpha, mu minus alpha, mu plus alpha. So this is the normal uniform distribution. And we can easily find that this uniform distribution is less peaked compared to normal distribution. So calculating kurtosis with the numerical summary table, as we see with the definition over here, we can get the kurtosis value as minus 0.2 and minus 0.5. So because they are negative, so we can say that the uniform distribution is less peaked or thin-tailed compared to the normal distribution. However, the double exponential distribution or the Laplace distribution this is the double exponential distribution with here. Yes. This distribution is high-peaked and fat-tailed compared to the normal distribution because the power of the exponential term for the normal distribution, we have x squared term here, especially 2 sigma square x minus mu square. However, anyway, this is the x square. However, this double exponential distribution has maybe 2 lambda over x minus mu. So its decaying ratio, the power of the exponential is proportional to the x. So Gaussian distribution is diminishing faster compared to this exponential distribution. So in other words, the exponential distribution has fat tail because it's diminishing less, slower than the normal distribution. So with this numerical summary table, we can calculate the kurtosis of the double exponential distribution. The value of the kurtosis from this numerical summary table is 0.296 and 0.726. They are greater than 0. So we can also know that the double exponential distribution is high-peaked and fat-tailed compared to the normal distribution. So this is the way how can we use the numerical summary table of the normal distribution. Numerical summary table for the kurtosis and mid values. Okay. And also the mid value of this double exponential distribution is the same, so we can easily infer that this distribution is symmetric. Okay, that is the all for the chapter 4, and see you on the next class. Bye.